When we see a label at the grocery store that says 100% pure mineral water, or look at a heavy stack of 24-karat gold bars, we assume we're looking at something untainted. But in everyday language, pure usually just means nothing artificial has been added. That gold is likely an alloy mixed with copper or silver to keep it physically hard. In chemistry, purity is absolute. A pure substance is a material with a strictly fixed, unchangeable composition. It is made of exactly one single type of element or compound, repeating perfectly down to the atomic level. The moment another substance enters that space, we have a mixture. A mixture contains two or more components physically occupying the same space, but they are completely free of chemical bonds to one another. Think about the water you drink. Chemically pure water consists of nothing but H2O molecules, but the water flowing from your tap is packed with dissolved salts, calcium, and magnesium. It is a mixture. The visible world is inherently messy. To locate true purity, we have to look past what our naked eye can see and categorize matter at the molecular level. Because mixtures lack chemical bonds, we classify them by their physical intimacy. We look at exactly how closely their separate components mingle. On one end of the scale, we have solutions. These are homogeneous mixtures, meaning their components are completely and evenly distributed. The dissolved particles are so small they are invisible to us. On the opposite end are suspensions. These are heterogeneous mixtures, where the particles are quite large. If you mix dirt into water, you can clearly see the suspended mud particles, and eventually gravity will pull them right to the bottom. In the middle, we find colloids. Colloids are deceptive. The particles inside a liquid, like milk, are larger than what you'd find in a true solution, but they are still small enough to defy gravity. They never settle out, making the liquid appear entirely uniform to the eye. This presents a practical problem in the lab. If a colloid and a true solution both look perfectly uniform in a beaker, how can chemists actually tell them apart? They use the Tyndall Effect. If you shine a laser through a true solution, the beam passes straight through cleanly. But if you shine it through a colloid, the slightly larger suspended particles scatter the light, making the exact path of the beam brightly visible. You can actually see this on a macroscopic scale when sunlight pieces through a dense forest canopy. The air is acting as a colloid, suspending tiny droplets of moisture and mist that catch and scatter the light. Our perception of purity is an illusion of scale. Knowing exactly how intimately a mixture's components interact dictates the precise tools we need to handle it. When dealing with true solutions, we are handling components that are so thoroughly dissolved they can't be seen or even caught by a physical filter. To understand what's in the beaker, we have to measure it mathematically. Every solution has two halves. The solute is the substance being dissolved, like salt or sugar. The solvent is the substance doing the dissolving, usually a liquid, like water, present in a much larger quantity. This graphic shows the formula chemists use to calculate concentration by mass. To find the mass percentage, you divide the mass of the solute by the mass of the entire solution and multiply by 100. So if you dissolve 50 grams of salt into 200 grams of water, you don't divide by 200. You divide by the total mass of the new mixture, which is 250 grams. 50 divided by 250 gives us a 20% concentration. Calculating concentration proves that we don't need to see a dissolved substance to know exactly how much of it is there. We can reliably track its mass and predict its chemical behavior. Because the components of a mixture are only physically occupying the same space rather than chemically fused, we can use their different physical properties to force them back apart. If a mixture has particles of varying densities, we can use centrifugation. By rapidly spinning the samples in a machine like this one, we generate forces that push the heavier, suspended solids straight to the bottom of the test tube. If we have two completely miscible liquids, meaning they have thoroughly dissolved into each other, we can separate them using heat. This process is called distillation. By carefully raising the temperature, the liquid with the lower boiling point will vaporize into a gas first, leaving the second liquid behind. That rising gas is then routed through a condenser, a cool glass tube that forces the vapor back into a liquid state. It drips out into a clean beaker as an entirely pure, separated substance. For more complex mixtures, like multiple colored dyes dissolved in black ink, we use chromatography. This technique separates components based on exactly how fast they naturally travel across a medium, like filter paper, when exposed to water. These precise laboratory techniques are the direct result of centuries of work by early chemists like Antoine Lavoisier, who spent their lives developing ways to isolate basic elements from their natural states. Matter is rarely pure on its own, but by studying how substances mix, dissolve, and react, we gain the ability to filter the chaos of the universe down to its purest building blocks.